This is Charlie Henning presenting my final PowerPoint on the Distributed Computation Framework project that I am doing for my capstone project. Here's a little background on the problem I'm trying to solve here. So my client has an application that he needs to run faster. It's a legacy application that is currently running a single thread on a 32-bit application. This means we have a lot of available resources on today's modern computers that we're not able to tap into because of the limited headroom on memory and because typical processors can service multiple threads at a time. Also, due to the nature of a legacy application, the architecture is very inflexible for this legacy application, and it's very prone to errors. So if you try to modify it excessively, it's very common that you will find issues in the code where you did not expect them. Currently, for my client, re-architecting the code is too great a risk due to the production and release schedule that he is currently under. He cannot afford to essentially do what I would consider the right thing and build a lot of this functionality into the application itself. So the objectives of this project, we need to retain all of the current functionality. Specifically, it needs to be a packageable desktop application. I should be able to send a disk to a user, they can install it and get all the functionality inherent with that program. We need to increase utilization of local area network resources, whether that is the machine that the user is actually executing the application on, or if it is the entirety of a local area network where we have several machines that we could draw on. And we also want to offer internet computation capability. So this means you could potentially borrow computational power from some other spot on the internet made available either through a particular company or cloud computing services, if you will. We also need to make the user interaction with this new project seamless. We need the user to be able to interact with the application the same way they would have prior to adding this capability. And then obviously, one of the largest objectives here is to actually increase the end user productivity. So the purpose. We discussed our objectives, but the purpose here is to distribute the workload across other computers that are currently being underutilized. The environment in which this legacy application operates frequently means that users will be defining a simulation, and when I say users, there's typically a group. So all of these users will define themselves a simulation, and then they will compute said simulation. Actually defining a simulation is a very low effort activity. Computing a simulation, on the other hand, requires a pretty enormous amount of computational work. Typically, it's a CPU-bound process, so it's not waiting for a whole lot of I/O off of the hard drive. This causes a giant waste of users' time, because what will happen is they'll define a simulation and then they will click compute, and that compute locks their application until it has completed. So one of our main purposes here is to decrease the amount of wait time that users experience when using the application. And we also want to provide a robust job scheduling system. This job scheduling is going to let us distribute that computation across multiple computers, so we get better utilization of computational hardware, and we're going to be able to return those results to the user hopefully much faster. The components that we develop need to be very easy to integrate. That goes back to the legacy system bullet on the last slide. We need this to be as seamless as possible as far as additional code required and footprint on the actual software. And then finally, the ever crucial retaining the ability to compute locally. If somebody should not have a local area network connection or an internet connection, they still must be able to utilize all functionality of this application, so we cannot inhibit that functionality. The design the client and I have settled on to make sure that all of our purposes and goals are met is a client-server application. So on the right here, you can see the general structure of the application. The legacy application is my client's pre-existing application. Everything in blue he will provide. The things in green are what I am developing here for this project. So there will be an interface boundary between the legacy application and my client application. The purpose here is to effectively allow the legacy application to import an assembly, in this case a jar, a Java archive file, and to use any of the functionality provided by the client application. So there will be an interface that exposes functionality that the legacy application can execute on. In this case, it will be to compute a job. So the legacy application will say compute job. It will send the relevant object, an XML object in this case, to the client application, which will forward that XML document to the scheduler application. You'll notice two gray icons here. These gray icons represent routers. I did that specifically to indicate that you could do this over a local area network or an internet connection. This scheduler application does not need to run local. It could run over the internet. In this case here, I would say this is a demonstration of a local area network where the scheduler application just exists on the other side of a network boundary. Finally, once you go through the scheduler application, you get to the server application with another interface boundary, and the customer provided computation application will actually perform the computation here. The intent of the customer provided computation application is to allow the customer to adapt this framework over time. So the framework is only providing the ability to distribute these jobs. The customer is going to, dictate how those computations will occur. Along with this framework, there's a messaging service. The client, scheduler, and server applications all support this messaging service, and that's serving as a means to identify where a job is in the queue or in the process of being computed. Additionally, the scheduler application provides load balancing. So if you have a large number of server applications, that scheduler will break the jobs up and send them out to the servers as applicable. Additionally, should a server disconnect while computing, the scheduler can reassign those jobs to a different batch of servers or server. Moving on, the server application itself, as we said, it interfaces with the user's compute application, and it's going to integrate into that computational application very similar to the way that the client does. They are both going to be files that you import through a Java archive. It also supports the messaging service. And the idea behind packaging these up as Java archive files is to make them very easy to import, like I said, with very little code that you need to actually implement, and then you can call into this functionality, and it also makes them cross-platform. Finally, for this project, I developed a series of artifacts, the project definition, the software project management plan, the software requirement specifications, the software design document, the risk management matrix, the work breakdown structure, which contains a sprint schedule, hour estimates, and cost estimates, all within the work breakdown structure document, and then finally performed a literature review where I reviewed all of the documentation that I read basically to get to this point in my design. That concludes the presentation for this semester's capstone. If you have any additional questions or concerns, please feel free to email me at chh7@students.uwf.edu. Thank you very much.